Across the flat farmland of central Turkey, the ground can look completely ordinary until the moment it fails. A field may be planted, irrigated, and crossed by tractors for years. Then the soil drops into a hidden cavity, leaving a steep-sided hole where solid land appeared to exist only moments earlier. These collapses are not confined to one isolated farm, and they are no longer being treated as a strange local curiosity. And Turkey's disaster agency has cataloged 655 sinkholes in Konya province, including 534 around Karapanar. The wider mapping project has recorded 684 across Konya, Karaman, and Aksaray. At the same time, satellite radar is detecting broad zones of land subsidence across the Konya closed basin, including places where the surface is dropping by centimeters each year. That is the current warning sign. But the title needs one important correction. A completely new sinkhole field is not suddenly opening across central Turkey. The region already contains an established and expanding sinkhole zone shaped by soluble rock, drought, falling groundwater, intensive irrigation, and the slow failure of underground cavities. And the most dangerous part is not always the giant hole you can see. It is the ground that is already moving before a hole appears. A study published in 2026 examined nearly a decade of satellite observations around Balık and Tursakan lakes in the northern Konya closed basin. It found an average downward movement of about 15 millimeters per year across the study area. In the most sensitive zones, the measured rate reached as much as 114 millimeters per year. And that does not mean every sinking pixel will become a sinkhole. Regional subsidence and sudden collapse are related hazards, but they are not the same process. Some ground settles gradually as aquifer pressure falls and fine sediments compact. Some cavities grow inside soluble rock and fail abruptly. In certain places, both processes operate together. This distinction is the key to understanding what is happening. Central Turkey is not being swallowed by one advancing front. It is experiencing a patchwork of hidden changes beneath one of the country's most important agricultural landscapes. Some changes are measured in millimeters. Others end in a collapse tens of meters across. The question is no longer whether the ground is moving. The question is where that movement will remain slow and where it may suddenly break through the surface. For documentaries that separate a real earth hazard from the most exaggerated version of the story, subscribe and stay with us. And what is happening beneath Konya becomes more alarming once you understand why water, rock, and farming are now working against one another. The Konya closed basin sits on the central Anatolian plateau. It is called closed because its surface water does not drain to the sea. Water enters through rain, snow, rivers, and underground flow, then leaves mainly through evaporation, plant use, and human extraction. That geography matters. In a coastal basin, some water can move outward through a river system. In Konya, the balance is more confined. When rainfall is low and demand is high, groundwater becomes the reserve that keeps cities supplied and fields productive. The aquifer begins carrying a larger share of the entire regional water burden. Konya is also a major agricultural center. Its broad plains support cereals, sugar beets, maize, and other crops. Irrigation turns a semi-arid landscape into productive farmland, but the water demand is enormous. Any surface supplies become less reliable. Farmers drill wells and pump groundwater from increasing depths. The result is not one simple chain in which pumping directly creates a hole. The geology has to be vulnerable first. Large parts of the basin contain limestone, gypsum, and other rocks that can dissolve when water moves through cracks. And over long periods, groundwater enlarges fractures and creates underground channels, chambers, and irregular cavities. Above those rocks lie layers of clay, sand, gravel, lake sediment, and soil. Some cavities are ancient. Some are still growing. The cavity can remain stable while groundwater partly supports the surrounding material. But when the water table falls, the balance changes. Water pressure decreases. Fine sediment can be carried into openings. Unsupported material begins moving downward. The roof may sag gradually, fail in stages, or collapse suddenly at the surface. These different pathways can produce very different shapes. A cover subsidence sinkhole may begin as a shallow depression, and the land bends downward over time, sometimes forming cracks around the edge. A cover collapse sinkhole can open rapidly when the roof of a cavity can no longer carry the material above it. A bedrock collapse sinkhole involves failure within the soluble rock itself. The official Konya inventory consists of the 655 sinkholes identified in the province. 331 were classified as cover collapses, 273 as cover subsidence features, and 51 as bedrock collapses. And that classification matters because the word sinkhole often makes people imagine one dramatic vertical shaft. In reality, the hazard includes subtle depressions, broad settling zones, hidden voids, and steep fresh collapses. And a feature that looks shallow can mark a much larger zone of weakened material below. This is why photographs alone cannot reveal the full problem. Aerial surveys and field teams can locate existing holes. Satellite radar can detect regional surface movement. Geophysical methods can search for cavities and weak layers. And groundwater wells show how aquifer levels are changing. Geological maps identify rock units where dissolution is more likely. Each method sees one part of the underground system. None can guarantee the exact hour when a roof will fail. The recent mapping shows that the hazard is no longer concentrated only in the most famous sinkhole district. Karapanar remains the center with more than 500 registered features, but sinkholes have also been documented in 11 other Konya districts. The wider AFAG project has extended into Karaman and Aksaray. That does not prove one continuous field is spreading evenly across central Turkey. It shows that the combination of vulnerable geology and groundwater stress exists across a wider area than the iconic images from Karapanar suggest. The landscape is connected by water demand. The collapses remain local. This is the first major reframe, and the visible sinkholes are not a moving army of holes. They are separate failures emerging from a regional system under pressure, and that pressure is measurable from orbit. Interferometric synthetic aperture radar, usually shortened to INSAR, compares radar images of the same ground taken on different satellite passes, and tiny changes in the distance between the satellite and the surface alter the radar phase. When hundreds or thousands of observations are processed together, researchers can map deformation across enormous areas. The technique does not photograph an underground cavity. It measures how the surface moves. A 2024 study used Sentinel-1 data from 2014 through 2020 through 2020, 2020, 2020, 2020 to examine the entire Konya and Orheic Basin. Researchers identified widespread subsidence with rates reaching about 90 millimeters per year in the satellite's line of sight direction. Areas subsiding by at least 10 millimeters per year covered thousands of square kilometers. The strongest sinkhole concentration and the strongest broad subsidence did not always overlap. Sinkholes were concentrated around Karapanar, where soluble formations in cavity development are especially important. Broadland subsidence was also detected around populated and heavily cultivated sections of the basin, including the central Konya area. This separation is crucial. A city can sink gradually without opening giant holes everywhere. A farm can collapse into a sinkhole even when the surrounding regional subsidence map appears less dramatic. And the two hazards share groundwater stress, but they respond to different layers and structures underground. Another study covering Konya province from 2018 to 2023 processed nearly 300 Sentinel-1 images and generated about 1.45 million measurement points, and roughly 40% of those points showed negative movement, indicating that subsidence affected a substantial part of the province. Measured line-of-sight velocities ranged from about 45 millimeters per year downward to 17 millimeters per year upward, and the map was not uniformly red. Some areas remained stable. Some rose slightly because radar motion includes local geology, reference choices, atmospheric effects, and the geometry of the satellite's view, but the pattern confirmed that ground loss was not restricted to a handful of circular holes. And then the 2026 Balık study added a more detailed picture of one sensitive zone near the southwestern side of Lake Tuz. Researchers processed more than 2,600 interferogram products from ascending and descending satellite tracks, and by combining those viewing directions and calibrating them with a fixed GNSS station, they estimated vertical movement instead of relying only on motion along one radar line. And the average subsidence was approximately 14.8 millimeters per year. That number sounds small until it is placed into time and space. And 15 millimeters every year can become 15 centimeters in a decade if the rate persists. Across farms, wetlands, salt marsh terrain, and lake sediments, uneven sinking can alter drainage, strain infrastructure, deform canals, and increase stress between neighboring ground blocks. And the average also hides faster pockets. The study identified deformation rates reaching 114 millimeters per year in areas sensitive to karst processes. Around 5,500 hectares on a carbonate-rich formation averaged roughly 50 millimeters per year. Another alluvial zone north of Bolog Lake averaged around 45 millimeters per year. These figures do not forecast a sinkhole. They show that the ground remains active, and the locations of the strongest movement also offered clues about cause. Deformation concentrated in agricultural land, natural grassland north of Bolog Lake, and salt marsh areas southeast of Tursuken Lake. The authors link some patterns to groundwater use and irrigation-driven karst processes, while other movement may reflect compaction in evaporite-rich wetland sediments. And the same downward signal can therefore have more than one explanation. That is why a satellite map must be read with geology, groundwater data, and field observations. And there is another limitation. Radar detects motion at the surface, but a cavity may be developing tens of meters below without producing a measurable signal above it. The roof can remain stiff until failure approaches. Vegetation can reduce the quality of radar measurements over cultivated fields. And plowing changes the surface. Moisture changes the radar response. A single satellite track also sees motion from an angle, mixing vertical and horizontal components. And researchers reduce those uncertainties by using long time series, 2 viewing directions, stable reference points, and GNSS stations. Even then, the final product is a deformation map, not an X-ray, and this explains why a quiet-looking location cannot be declared safe from one green pixel. It also explains why a red pixel cannot be labeled an imminent sinkhole. The most defensible interpretation is layered. A persistent downward trend raises concern, and karst-prone geology raises it further. Falling groundwater and nearby collapse history add more evidence. Surface cracks, depressions, or geophysical anomalies may justify detailed field investigation. Risk builds through convergence. Prediction remains limited. This difference is not merely academic. Nay, false prediction could make farmers abandon land unnecessarily, lower property values, or create panic around a road or village. A false reassurance could leave workers and equipment exposed to a collapse that develops without an obvious warning. The goal is not certainty. It is better prioritization. Then the Kanya Basin contains old lake beds filled with fine sediment. When groundwater is removed, the pressure inside pore spaces declines. The weight of overlying layers transfers more strongly to the sediment framework. Grains rearrange, compress, and lose volume. And this is aquifer system compaction. Some compaction may be permanent. Even if water levels recover, the ground may not rise back to its original elevation because the sediment structure has already collapsed internally. The basin loses not only surface height, but also part of its future water storage capacity. And karst collapse adds another mechanism. Water moving through carbonate or gypsum dissolves solid material and enlarges underground openings. Pumping changes hydraulic gradients, which can accelerate the movement of water and sediment. Repeated seasonal rises and falls can destabilize material above a cavity. Heavy rain can also contribute in a surprising way. Rain is essential for recharge, but when a cavity roof is already close to failure, wet soil becomes heavier. Water can enter fractures and mobilize loose sediment, and a collapse may occur after a rainy period, even though long-term drought and groundwater depletion help create the unstable conditions. This is why one event cannot be blamed on one day of weather. The hole opens suddenly. The failure develops slowly, and that hidden delay makes sinkholes difficult to communicate. A road can cross weakened ground thousands of times without a visible problem. A field can be harvested normally while sediment is migrating into a cavity below. The final collapse may look like the beginning of the disaster when it is actually the last stage. And the Kanya region contains both ancient sinkholes and modern ones. Some older features are enormous landscape elements with lakes or dry floors, and they formed through long natural karst processes. Newer cover collapse features can appear within actively cultivated plains and may be shallower but more disruptive because they intersect farms, roads, power lines, irrigation systems, and settlements. And the increase in mapped features does not mean every one formed during the latest drought. Improved surveys discover older sinkholes that were previously undocumented. Mapping projects expand into new districts. Satellite images reveal subtle depressions, and local reporting makes collapses more visible, but better detection is not the entire explanation. Researchers and local experts have repeatedly documented new collapses, ongoing enlargement of existing holes, declining groundwater, and expanding subsidence. The hazard inventory is growing because the monitoring is improving and because the landscape is continuing to change, and those two facts must be kept together. The official project recorded 655 sinkholes in Konya, 20 in Karaman, and 9 in Asaray. All were reported in rural or agricultural settings, and officials said the mapped features had not directly threatened a settlement at the time of that update. That statement is reassuring, but it is not a declaration that the risk is harmless. And the same official meeting that reviewed the sinkhole issue described it as a regional disaster risk with economic and social consequences. Authorities, universities, municipalities, and technical experts discussed how collapses could affect settlements, farmland, and transport routes, and called for continued coordinated monitoring. The problem is being treated as a planning issue before it becomes a larger emergency, and that is the correct scale of response. Not panic, not dismissal. The human stakes begin with uncertainty. Farmers may know that a cavity exists somewhere beneath a field without knowing when the roof could fail. A geophysical survey can identify suspicious zones, but underground voids can be irregular, layered, partially filled, or hidden below thick sediment. One location may remain stable for years while another collapses with little surface warning. The economic stakes extend beyond the area swallowed by a hole. A sinkhole can divide a field, block machinery, damage irrigation, lower land value, or force a farmer to abandon a productive section. Broad subsidence can change the slope of canals and drainage systems, and a small difference in elevation across a road or pipeline can create repeated structural stress. Then there is the water paradox. Agriculture depends on groundwater. Pumping that groundwater can deepen the hazard-threatening agriculture, and reducing extraction sounds simple from a distance. But the basin supports communities, food production, and established farming systems built around irrigation. And changing that system involves crop choices, water pricing, legal wells, unlicensed wells, efficient irrigation, monitoring, and alternatives for farmers whose income depends on water-intensive production. This is not only a geological problem, it is a water governance problem written into the ground. The 2025 satellite gravity study made that connection explicit. Its authors compared known sinkhole locations with broad geological signals and argued that groundwater use in and around the Konya Closed Basin must be controlled. They also called for public awareness and a shift away from traditional farming methods dependent on excessive irrigation. Gravity data cannot map individual small cavities at the required resolution. What it can do is help outline geological units where known sinkholes cluster. Combined with existing inventories, those patterns can guide future susceptibility mapping. Susceptibility is not prediction. A susceptibility map identifies where conditions are more favorable for sinkholes. It cannot identify the exact field that will collapse next Tuesday. It helps authorities prioritize surveys, land use review, road planning, and detailed investigation. That limitation must be stated clearly because dramatic maps can create false certainty. A red zone does not mean every point will fail. A green zone does not mean no hidden cavity exists. And the most useful monitoring system layers multiple kinds of evidence. Satellite radar reveals broad movement. GNSS stations provide precise ground control measurements. Field teams record dimensions and classify collapse type. Electrical resistivity and other geophysical tools can detect contrasts linked to cavities, water, or disturbed sediment. Boreholes provide direct but highly local information. Groundwater monitoring adds the missing clock. When water levels fall rapidly during irrigation season, aquifer pressure changes. When pumping slows, levels may partly recover. And comparing those cycles with seasonal deformation helps researchers distinguish reversible movement from permanent compaction and identify areas reacting strongly to extraction. Falling water, accelerating surface deformation, and real ground rarely behaves that neatly. Some sinkholes open without obvious cracks. Some cracks never become sinkholes. Vegetation and cultivation can hide small depressions. Radar coherence can be weak over actively changing farmland. A cavity may sit below the resolution of regional measurements, and this is why researchers cannot honestly promise exact sinkhole prediction. They can reduce surprise, they can update inventories, restrict access around fresh collapses, investigate deformation near infrastructure, and make groundwater policy reflect the physical limits of the basin. The strongest solution is also the hardest: restore balance between extraction and recharge. Efficient irrigation can reduce losses, but efficiency alone does not guarantee lower total use if saved water is used to expand production. Less water-intensive crops can lower demand, but changing crops alters markets and farm income, and closing illegal wells can reduce pressure. But enforcement is socially and politically difficult. Artificial recharge may help in selected areas where clean water and suitable geology are available. It cannot refill an overdrawn regional aquifer without a reliable water source. Transferring water from another basin can create new ecological and economic trade-offs. There is no single engineering switch. The ground is responding to decades of accumulated decisions. That is the midpoint reframe. Sinkholes may look like isolated geological accidents, but the expanding pattern is a physical record of the basin's water budget. Every new collapse reveals a local failure, and the subsidence map reveals the regional imbalance. This also explains why the final title uses the word zone instead of field. A field suggests one newly opened cluster with a clear boundary. The evidence shows something broader and more complex. An established concentration around Karapanar, additional mapped features across other districts and neighboring provinces, and separate subsidence zones extending through agricultural and populated parts of the basin. And the zone is expanding in the sense that mapping and new collapses are appearing across a wider geography. It is not expanding as a continuous underground cavity. The ground is still sinking, but not everywhere at the same rate, and those distinctions do not reduce the urgency, and they tell us where the urgency belongs. The next major hazard may be a spectacular cover collapse in a field. It may also be slow deformation beneath a road, canal, industrial area, or urban edge. A giant sinkhole attracts cameras, and a few centimeters of uneven subsidence across a wide area can create a much larger cumulative cost. Scientists will be watching several signals, and first is the sinkhole inventory. Whether new cover collapses continue appearing beyond Karapanar, and whether existing features enlarge. Second is groundwater, how far levels fall during irrigation and how much they recover afterwards. And third is deformation, whether in SARE time series show stable rates, acceleration, or migration into new areas. They will also watch the relationship between rainfall and collapse timing. A dry year can increase pumping, while a later wet period can load unstable roofs. The dangerous combination may not occur during the driest month itself. And finally, they will watch infrastructure and settlement exposure. A basin can contain hundreds of rural sinkholes without a mass casualty event, but risk changes sharply when deformation approaches a home, highway, railway, pipeline, or dense urban district. As of the latest official mapping, authorities reported no mapped sinkhole directly threatening a settlement. That boundary must remain in the story, so must the reason for continued monitoring. The absence of a current disaster is not the absence of a developing hazard. In central Turkey, sinkholes are not evidence that the entire plateau is about to collapse. They are not caused by one earthquake, one storm, or one underground river. They are the result of vulnerable geology interacting with groundwater decline, sediment compaction, karst dissolution, irrigation, and climate pressure. The science does not support a countdown. It supports a warning about trajectory. The basin is losing groundwater, and large areas are subsiding. Hundreds of sinkholes have been mapped. New collapses continue to appear. One more boundary is essential before the story closes. And the phrase, "the ground is still sinking," describes measured deformation, not a single uninterrupted downward motion across the whole basin. And SAR rates are averages over defined time windows. The location can sink faster during irrigation season, slow after pumping decreases, or show after pumping decreases, or show temporary movement linked to soil moisture and temperature. Long-term trends become meaningful only when repeated observations point in the same direction. This is why the newest studies are important, even though their satellite records end before publication. The 2026 paper does not claim that every measured rate continued 2026. It shows that deformation persisted across the 2014 to 23 record, and that the physical conditions responsible for it remain present. The official inventory and continuing field reports provide the current context around that measured history. A responsible documentary must keep those clocks separate. The inventory describes what has been mapped. The satellite record describes how the surface moved during its observation period. And the mechanism explains why continued groundwater stress can sustain the hazard. None of those alone predicts the next collapse. Together, they justify continued concern. The same discipline applies to numbers. And the 655 sinkholes in Konya are not 655 identical open pits. The inventory includes different collapse mechanisms and forms. Some are large and steep. Others are shallow depressions or cover subsid features. And counting them together is useful for regional planning, but a thumbnail that displays hundreds of giant black holes would be false. Likewise, the maximum subsidence rate is not the basin average. The 114 millimeter figure belongs to localized sensitive zones in one study area. Most of the landscape moves more slowly or remains comparatively stable. The danger comes from unevenness. Neighboring areas responding differently to the same water and geological pressures. That unevenness can bend a canal before anyone notices a regional change. It can create a fracture at the margin of a settling field. It can redirect surface runoff toward a depression and increase loading over a weak roof. It can also leave a stable-looking island between two sinking zones. The future of the basin will depend on whether monitoring becomes continuous enough to capture those transitions and whether water use changes before the deformation becomes harder to reverse. And the sinkholes are the most visible evidence. The water budget is the deeper story, and the deeper budget is the deeper story, and the deformation map is the bridge between them. The final image is not a dramatic hole, it is a flat field at sunrise. A tractor moves across the surface, and irrigation lines stretch toward the horizon. Nothing in the landscape reveals the exact location of a cavity or the depth of the water table. To the eye, the ground is still, but a radar satellite passes overhead and compares that field with thousands of earlier observations. A cluster of pixel shifts away from the spacecraft. Millimeter by millimeter, the surface is lowering. Below, groundwater moves through solidum. Below, groundwater moves through soluble rock. Sediment slips into hidden space. A roof carries weight it may not carry forever. The land still looks solid. The measurements